All right. Thank you for the introduction. Hi, everyone. My name is Haishan. I'm a software engineering manager at Meta. Very happy to be here, and it's really great to see so many people interested in Triton and working with Triton. So today I'm giving a tutorial on creating a MLIR pass for Triton. So in this tutorial, I'll provide a taste of working with MLIR and its usage in the context of Triton compilation. This tutorial will not assume any compiler background or prior knowledge. It will assume you've looked at some Triton kernels before, but we'll walk through the kernels in quite a bit of detail. So not a lot of assumptions on prior knowledge. Here are the topics that we'll cover. We'll talk about MLIR background at a high level. We'll look at the Triton front end, some example Triton kernels, and the front end Triton IR that it generates. And then we'll dive into the main example of this tutorial, in which we'll create a MLIR pass for Triton. All right, so let's start with some background on MLIR. As many of you already know, MLIR stands for Multi-Level Intermediate Representation. It was originally a project started within Google by Chris Latner, Mehdi Amini, and many others. On the slide, I linked a paper that folks has published on this project. In this paper, they mentioned one of the main motivations for the project was that people observed even within Google, within the domain of ML machine learning compilation, there were a lot of repeated work, and due to various resource constraints and so on, the wheels were often reinvented and sometimes re-implemented in a suboptimal way. And the goal of MLIR is to really create a reusable compiler infrastructure that is generally applicable to many, many use cases. And as a user of MLIR framework, I would say this goal is largely achieved today. If you take a look at the MLIR website and look at all the different use cases, you will see a large number of compiler projects that range from more traditional compilation to I would say more novel use cases such as high-level synthesis, language compilation for hardware design. So what is MLIR today, right? So if we dive into the code base, you'll see that it's really a very, very usable framework to build compilers. It comes with a large number of existing dialects, types, transformations, and analysis. And perhaps more importantly, it is very extensible with custom dialects, types, transformations, and analysis. It has its own pass infrastructure, diagnostic tools, testing tools, and so on. And one more important point I want to mention is it is also very easy to integrate the MLIR compilation flow into a LLVM backend compiler for low-level architecture-specific optimizations and code generation. So in case people have not seen what MLIR looks like, I just want to spend a couple minutes to just walk through what a very simple IR could look like, and later on we'll see more examples. So what on the screen is probably what a simplest IR could look like. It is doing a add operation. The arith part specifies the dialect. So this operation comes from a dialect called arith. The operation name is addF, or add floating point. It takes two operands, %0 and %1, and the result that it produces is %2. On the right-hand side of the column, we specify the operands and result type. In this case, they are tensors of 1024 floating point 32s. There's only one field there because all operands and result happen to be of the same type. So taking a step back, what you'll see is, or what I want to mention is, MLIR uses the notion of operations rather than instructions. So operation can basically mean anything from something that's complicated as a 3D convolution on tensors and filters and so on, or it could be as fundamental as integer arithmetic operations. Operations are opaque functions to MLIR. So what that really means is we can define operations to mean whatever we want them to mean. But at the same time, they'll have standard interfaces so that MLIR passes can work with operations that the authors of the past may have never seen before. You will notice that the IR is represented in SSA form. SSA stands for single static assignment. What that means is essentially each operation produces its own result, and we don't reuse names. So no other operation in this IR would produce another %2. This simplifies a lot of the compiler analysis. But what I would also mention is MLIR's SSA form might be a little bit different from what you see in textbooks SSA definition. Specifically, there's no notion of a fine node, but rather this is a lot of the complexities were handled differently using block arcs and control ops return values. And lastly, I want to mention that what's on the slide really is as simple as an IR could potentially go. But for folks who are more interested, I linked some slides that presented more comprehensive examples. You will see like operations could have various attributes. It can contain debugging information, and so on and so forth. All right. So I mentioned a lot of names, a lot of different concepts. But how do these things sort of compose together at the MLIR framework level? So one important concept to call out is the notion of dialects. A dialect is typically a collection of operations, types, attributes, related transformation passes, analysis, and etc., usually for a single purpose in a single namespace. I want to mention that multiple dialects can coexist within one module, and that's very much to the hybrid or multi-level nature of MLIR. In this last bullet, I'm listing some example dialects. Arith, math, the name are pretty self-explanatory. Func dialect defines operations that you will use to define functions, function calls, returns, and so on. LVM dialect defines a lot of the lower level operations that typically have a one-to-one mapping to LVM IR, and it's very, very useful when you integrate with backend compiler. memref dialect defines operations for us to easily work with, memory allocation, deallocation, views, and so on. Types. So MLIR supports both built-in and custom dialect types, and I listed some examples below. And the last important concept that I want to mention is the notion of attributes. They are essentially in place constant data on operations. So some examples of attributes are comparison predicates, for doing a equal to, not equal to comparison. And in a Triton-specific example would be if we're performing a boundary check on load or store addresses. I think this is the last slide on MLIR background. So how do these things put together, right? How do we use MLIR to actually represent a program? So MLIR uses a recursively nested IR structure. What that means is a single operation can contain multiple regions, and each region can contain multiple blocks, and each block can again contain multiple regions, and it recurses from there. So one example to demonstrate this is a Triton reduce op can potentially contain multiple operations in its body. And that allows us to express that we want to perform a relatively complicated reduce operations, even just with a single pass on the data. There are many different ways to navigate the IR structure, in addition to just iteratively visit each operation in program order. For one, MLIR provides mechanism to walk the recursive IR, and this is something that we'll see later in example. And MLIR also allows users to leverage the SSA nature so that we can easily traverse the dev use chains. The figure on the right, and apologies, I realized I lost the citation. I took directly from the MLIR website, and showcases some of these aspects that I just mentioned. So in this specific example, we have a block. which again, contains many operations. There's a begin and end pointer that marks the first and last operations in the block. A block can also have multiple block arguments. Within the block, we can again have multiple operations. Each operation can consume one or more operands or multiple operands, and it could produce multiple results. You'll notice that these operands are essentially just pointers to values. So, in the case of the middle operation, right, one of the values have 2 operands, and it's very easy for us to leverage the SSA nature to say, what are the uses of this value. And again, we'll see more examples down the line. Now let's switch gear to talk about more Triton-related background. So thanks to Karen, he covered a lot of great background, specifically, how the front-end compiler is structured. What I want to mention more is, after the initial front-end compilation, the Triton kernel will get translated into, MLIR format using Triton dialect and some of the other standard dialects. And as we heard earlier, Triton defines a set of dialects, and the Triton dialect is one of them. Here on the screen, I'm showing some of the things that comes in Triton codebase that makes this dialect to work. In Triton types, we define a bunch of types that Triton operations can work with, from the things that are more familiar, like floating 32, integer 16, to some of the narrow precision data types. We also define integer types, tensor types, pointer types, so we can perform memory access on. In Triton ops, we define operations that often have one-to-one mapping from the language level constructs, like add pointer, where a key operation that we use to perform pointer arithmetics, loads, stores, dot to perform gem operations, and so on. And the list goes on. The Triton dialect also defines quite a few transformation passes to perform optimizations. It defines various interfaces and attributes for MLIR passes to work on the corresponding types and operations as well. So let's look at, in the next couple of slides, let's look at how a Triton kernel gets translated into the front-end IR. We'll walk through this example line by line because this is an example that we'll use for the rest of the tutorial. So it might look quite familiar. It's actually a slightly simpler version than what Karen showed earlier. This kernel is trying to do a tensor scalar addition. So we define this add kernel. It has 3 arguments: x pointer or input pointer, y as a scalar value, and the output pointer. The block size is, again, a compile time constant. In a kernel body, we first take the program ID. We then use the program ID to calculate the offset starting from which this program is going to process the data. The offsets variable is a per element offset, so we calculate that by adding the block start with a range that starts from 0 and ends at block size -1. So to load the data, we add the base pointer, x pointer, with the per element offset. That creates a tensor of pointers, and from that we can load the data. To actually perform the arithmetic operation, we simply say x plus y, and what we're doing here again is we're adding a vector of block size with a scalar value that produces our output, and we're writing that back into memory. So this is what's on the screen is what the Triton front end would generate, and let's walk through this again. But at a very high level, you will see right away that the IR actually uses operations from multiple dialects. We see some operations from arith dialect to express constants. Add operations to perform either pointer arithmetics or numeric operations. But again, let's dive in. You'll see that the function is now from a TT dialect or Triton dialect func operation. we have the kernel name, and we shed the compile time constant, but we still have these 3 arguments. Now it's very clear the types of each argument. Arg0 or x pointer is a Triton pointer to float 32s. Arg1 or y from the prior slide is again a scalar of float 32, and the output pointer is again just a pointer to f32s. Within the kernel body, we have the constant operation. So in this example, I arbitrarily chose a block size of 1024. So that's why we happen to have this constant here. But %0 is the program ID, which has a one-to-one mapping to what we saw earlier. We multiply using arith.mul_i to multiply the program ID with our block size, and that calculates our per program ID offset. tt.makeRange corresponds to the earlier tr range that creates a per element offset. And what's interesting here is, even in the prior example, right, we're directly adding the program ID, or rather the per PID offset with this range. But here in %3, we're actually splatting %1, which again is the per PID offset. And we actually add the result of this splat with the result of the make range to produce %4. You can see this pattern repeats itself in calculating the actual tensor of pointers. So we are splatting arg0 or x pointer to create another 1024 tensor of pointers, and we're using tt.addPointer to actually calculate the per element address. In calculating %7, we perform tt.load to actually perform the memory load. And then you can see the pointer happens yet again, right, where we splat arg1, which is our scalar value, into a tensor of 1024. And we use arith.addf to actually perform the arithmetic operation. All right. So now let's dive into the main example of this tutorial. So with all the background in mind, right? What we want to use as an example in the tutorial is we want to create a pass that replace tensor operation with tensor scalar operations when possible. So specifically, as you may remember from the last slide, we see these repeated operation sequences where we would splat a scalar to create a tensor, and then we would use the splat result to perform a element-wise operation. And the goal for this new pass that we're creating is to create this to define and create this new instruction. Here I'm calling it myarith dialect .ts. This new operation will take a tensor as the first operand, a scalar as the second operand, and it will produce the tensor result. So why we might want to perform such a transformation? So many hardware actually natively support vector scalar operations, but at least at the arith dialect level, there's no built-in or native support for this. By performing such an optimization, we'll have fewer instructions to run, which is in general a good thing. We can also avoid potentially materializing %8 in this case, which are results of splatting scalars, and that can help potentially reduce on-chip memory pressure, reduce register pressure, and potentially help with the performance and the power. So in the rest of this tutorial, as I mentioned, we'll define a custom myarith dialect. We'll also define a custom add TS or add tensor scalar operation, and we'll define a simple pass to achieve this rewrite of a splat add operation sequence with our newly defined operation. So first things first, we like to start by defining the dialect. And just as a reminder, MLIR dialect is a group of related operations, types and attributes, transformation passes, and so on in a single namespace. We can define new dialects either using C++ by inheriting from MLIR dialect, or we could do it with TableGen, which is a handy tool for us to generate lots of codes. And that's the approach that we're taking. So we'll be creating a myarith dialect.td file. In that, we'll define myarith dialect, which inherits the MLIR built-in dialect. We'll give it a name, a C++ namespace, and a short description. And that's all it takes to create this dialect. Next, we'll define our new operation. So we're doing this again using TableGen. We'll create a new file called myarith.ops.td. Inside of it, we're defining myarith.ops, which are essentially all the operations in myarith dialect. So we, again, inherit the base MLIR op, and we specify the dialect name, and we're basically just passing the mnemonic and the traits through. To actually define the new operation, we just need to define this myarith at tensor scalar op. We specify the mnemonics to be @_ts. We provide a summary, and in the arguments, we will explicitly specify the two input types, right, or the operand types. The tensor value is a ranked tensor of any floating point integers. Any floating points or integers. The scalar is just a scalar float or integer, and the result is of the same type as the tensor. Lastly, we provide a assembly format string so that the TableGen will generate a nice printer and parser for us, and our generated IR will be nice to look at. So we talked about TableGen a whole bunch, right? So what kind of C++ code does that actually generate? So here I grabbed a couple of screenshots for us to get a better idea. You can see we're defining this class called @scalarOp, and it inherits a bunch of traits in addition to, or rather, it inherits from the base MLIR op, and it already has a bunch of traits specified, all thanks to TableGen. We know from the definition that for example, it has no regions, it has one result, 0 successors, and so on. The TableGen also generates handy functions for us to work with the operation. We have nice getter functions, for example, getTensor and getScalar, that help us to grab the value that each @ts operation uses. And lastly, there's a handy function at the bottom of the screen that shows you how do we build a new @ts operation. To build this new operation, besides the boilerplate, we just need to specify the type of the result and the two values, the tensor and the scalar, and that's essentially all it takes. So coming back to finish, our example, the next thing we want to do is, of course, we actually want to define our path to do this rewrite. So here, we're using TableGen again. We create a new passes.td file. We define our convert Triton to myarith pass. We give it a brief summary, and in the dependent dialects section, we specify which dialect we will generate operations from in this pass. So in this case, it'll be our newly defined dialect. Now, to actually define this pass, we'll use the TableGen generated boilerplate code. And that greatly simplifies, the amount of code that we actually have to write as a human. But the main logic essentially is summarized, in the screenshot below. So the main function is this run-on operation, in which we will use the capability that MLIR provides for us to hierarchically walk the IR structure. So you can see we call get operation to grab the module op or the root op of the program, and then we can walk this recursively structured IR and call our rewrite splat at op only on Triton funcop, which, as you might remember, is the function operation that encapsulates our entire program. Inside this rewrite splat at op function, we're again, walking the IR structure. This time, we actually want to rewrite or we want to pattern match the splat op, and that's what this lambda defines. You will notice that in the for loop, we're iterating over the users of the result of splat. So that showcases, in MLIR how easy it is to traverse the dev-use relationship. For each user, we check if it's a arith at f operation, and if we find a match, we know we found the pattern that we're looking for, and we can go ahead and rewrite this operation. To actually perform the rewrite, we essentially only have to call the build function that I showed earlier. So we instantiate our builder. We figure out which is the tensor operand. We already have the scalar operand as a parameter to this function. So that gives us all that it needs to create this add tensor scalar operation. The last thing that this function does is it replaces the use of the result of addf op, the original arith dialect op, with our newly created operation. And that essentially completes our rewrite. So putting this all together, what we have achieved so far, right? So we defined a new dialect called myarith. We defined a new operation add ts. We created a new pass to manually pattern match the splat add sequence and rewrite them with our newly defined operation. To get this example to work, of course, there are some other changes that are required. We need to register the corresponding dialects and the passes, in this case in Triton opt, which is the pass driver that the upstream Triton already built. We could, of course, also do this on our custom pass driver. We need to make a few CMake changes so that we'll actually build our new files. And I include a link to a patch to enable this example in case you want to try it on your own. To see the custom passing action, you basically can walk through, in this specific setup, you can just walk through the normal Triton setup that Karen also mentioned earlier. And you can call the Triton or the MLIR pass driver Triton opt. You specify the name of the pass that we're trying to invoke, provide an input file, and it will supply the output file. Apologies, I didn't realize that we can't click the links, so I'll just describe what the output file looks like. What you will see in the output file is that there is a the new operation that we have created, insert right in the middle of the operation. It will take the scalar argument and the vector that we loaded from memory, perform the add tensor scalar operation, produce the result. What you'll also see in the output is that the result actually propagates to the tt.store, which is indeed what we intended, so that we can write the result back into memory. What you will also notice, from the description so far, and also if you examine the first output, is that we never actually got rid of the operations that we're replacing, right? So we're replacing this splat add sequence. Those two operations are still in the first output file. So to complete this example, what we could do is we could either go back to our rewriting pass, making sure that these two operations have no other uses, manually delete them, or we could just call the canonicalization pass on top of our newly created pass, and that will remove all the values that have no uses and also no side effects. So in this tutorial, we walk through a very simple example on how to do a rewrite. There are many other considerations, if we're to do this for real, right? Specifically, when we define the operation, we typically would want to specify verifiers. In this example, we might want to check, if the tensor operand is a tensor of floating points. The scalar better also be a floating points. This so that we can, fail at the earliest possible time to catch errors. We might want to define a better assembly format so the generated code is, or the printout is more readable. we might want to specify the correct side effects. So in this case, we're not really writing memory, for example, and the correct interfaces, so that canonicalization passes can also work with our newly defined operation. For the sake of this demo, we are using a very manual pattern matching and rewriting process. I want to mention that MLIR has a lot of existing established tools for us to achieve that goal. Specifically, we could use pattern rewriter. We could also use TableGen to create rule-based pattern matching and rewriting logic, and that will essentially eliminate any sort of manual codes. We're calling canonicalization, separately. There are arguments to be made in, calling that within the path that we created, so that our top-level path structure is clear. It is not always so. In this example, we're doing this rewriting at the Triton IR level, but depending on the compilation pipeline that you're working with, it typically takes quite a bit of thinking to figure out what's the best place to perform such a transformation. So, for example, you might want to do this after the operations have been vectorized to the architecture you're targeting. Lastly, we mentioned earlier, right, in the example, we saw this repeated splat add sequence. If we were to materialize the tensor of pointers, we could potentially extend this rewrite for pointer arithmetics as well. So with that, I have finished all the materials I have. I included a couple links for references in case people want to look into this topic further. Thanks a lot.